Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Abhishek Panigrahi from Princeton University, who will tell us about the power of forward passes through transformers. So as I always do, I offer to watch the chat. So if you have a question that you'd like me to ask or to have evaluated, put it on the chat and we'll take a look. And you're happy with having questions during the talk, right? And then there'll be some minutes for questions at the end. So with that, Abhishek, please.
Yeah. Okay, sorry. All right, sorry. Let's start. Hi, I'm Abhishek, and I'm a PhD student at Princeton University working with Sanjeev Arora. I work mostly on the understanding deep neural networks, and now I'm looking at LLMs. Today, I'll be talking about on the power of forward passes through transformers. Well, everyone here is like familiar with language models, and the paradigm of language models is to first train them on lots of data and then infer them for a downstream task. So these models have shown amazing performance in a lot of datasets, and have shown extremely good like human level performance in a lot of professional and academic exams. Now, the question that comes up with all this performance that these models show is that what possible mechanisms do these transformers use during inference, and how can we relate them to pre-training? I'll try to explain this question in two interesting settings. The first setting will focus more on masked language models, which were like BERT, which were pretty popular before the pre-GPT era. This work is in collaboration with Ayu and Sanjeev at Princeton University and Rong from Dept University. All right, so this talk will have four major sections. First, I'll give a brief into what masked language models are. Then I'll talk about grammars to model language. Then I'll present our major theoretical claims. And finally, I'll show some experiments to support our theory. All right. So masked language models, or BERT, most specifically BERT, was a descendant of a transformer architecture where you had a stack of transformer layers on top of each other. Each transformer layer was made up of an MLP module and an attention module. But the main ingredient that was used in these models compared to previous architecture was the attention head. Let's give a brief on what an attention head does. It takes in a sequence of inputs, creates a query, key, and value vector at each position using transformations on the embedding at that position. And then it computes attention scores between different pairs of tokens using the query and the key vector. And finally gives an output, which is a combination of the value vectors using the attention scores. The key ingredient that was used to train this model was the mask language model loss, where given a sentence, you mask out few words in the sentence and ask the model to fill in the word. Right? For example, I mask a car, the model is asked to fill it, and it can fill it with it can fill it with have with some probability 0.04 or saw at 0.05, but animal probability should be 0. And the other ingredient here was the uses of bidirectional attention, where each token could look into the representation of the future token to create its own. For example, when I create the representation of the word I, it could look into the representation of word car to create its own representation. So this was a bit prior into what MLM or this BERT model was, but let's dive a bit into what people used to do pre-neural network. Well, the community used to model language using explicit grammar rules. For example, if you have a sentence like I have a car, you break each token in the sentence into different parts of speech, and then try to learn the dependencies between these parts of speech using a tree-like structure. And these grammars were formalized with context-free grammars or PCFGs. Let's give a brief into what a PCFG is. Well, a PCFG has 4 main components. First, it has a vocabulary, which contains all the words of interest in your corpus. Next, it has a set of non-terminals. For example, in this case, it could have been the non-terminals or the parts of speech that you use to break the sentence into. It has a set of rules where a noun phrase is mainly composed of a determinant and a noun, or a verb phrase is composed of a preposition and a verb. And it has rule probabilities. Like, what's the likelihood that a noun phrase breaks into a determinant and a noun is probably much more likely than the probability that a noun phrase breaks into a verb and a noun. So suppose we assume that there was a PCFG underlying your data, then the way you would create this data from a PCFG is to start from a special non-terminal called the start non-terminal. And then you would just replace non-terminals in generation with non-terminals or tokens given by rules. So the way my previous sentence, I have a car, could have been generated under this model is you start with the start token, then it breaks down into a noun phrase and a verb phrase. Then verb phrase breaks down into a verb and a noun phrase. Then noun phrase breaks into a determinant and noun. And finally, each of them break down into a token according to the production rule. And then say you had this grammar, say you could learn this grammar on the corpora, say you had access to this grammar, the most important operation then becomes parsing. So the motivation of this operation is to find the most likely tree of generation rules underlying a given sentence. For example, let's say we had the same sentence that we have been looking at before, like I have a car, and suppose these are the 3 possible trees that could have generated this sentence. There would be much more, but for visualization, let's say we have this tree. Then you would pick the tree that is the most likely under this grammar. And the way to do it is to find the tree that maximizes the product of probabilities of the generation rules underlying the tree. So if your grammar was correct, it would choose the first tree compared to the rest. Huh? NP is noun phrase, VP is verb phrase. So these are like parts of speech defined by this grammar. Like a verb phrase is mostly made up of a preposition and a verb, but it can be made up of other rules as well, and that is given by the set of rules that you define in the PCFG. So a noun phrase is made up of determinant noun with some probability 0.4, but it could have been made up of something else, and that's all given as a part of rules and the rule probabilities. Okay, Okay, so the question that we asked in this paper is that can BERT perform similar parsing inside without having to explicitly learn the grammar during pre-training? Well, empirically, it has been shown to be the case because previous works have shown that you can train simple neural networks given the BERT contextual representation to infer or to parse to give parse trees with a very high success rate. It's 80% success rate. You can think of F1 score as some sort of success rate of parsing using BERT. And the way they did was to take pairs of words, pass the contextual representation to a very simple layer, simple linear layer or dual layer NN, and predict the common ancestor depth. So, for example, in this sentence, I have a common ancestor depth as a start terminal, which has a depth of 0, have an A has depth of 1, A and car has a depth of 2. And then once you can predict all this common ancestor depth, you can recreate the tree. Okay, so the question that follows this observation then is, why is BERT able to parse even though it wasn't asked to explicitly learn the grammar at pre-training? Yeah.
In this example, why does it have A as 1 and car as 2?
This one?
Yeah, like in the tree.
Our car, the common ancestor depth is non-press, which has a depth of 2.
Or depth from the root.
The depth from the root, yeah. You can do it from the bottom as well, so it's fine. Yeah. Oh, yeah.
Is it for arrange over pairs of tokens, or is it for the full sentence?
For the full, actually, it's this accuracy number is like how well you have predicted the tree, and the prediction is made on the basis of number of spans that you could predict in the tree. So if you could predict A and car kind of come together to form this subtree, have a car have come together to form a subtree, and then I have a car. So it's like it's trying to predict all the possible edges in the tree.
So it's like an and of all these.
Yeah, yeah, and how much you could predict. Okay. All right. So this paper takes a step forward, understanding this phenomena by assuming that there is the data generated by English language is actually generated by some PCFG. And under this assumption, we show the expressivity of moderate-sized BERT models to apply approximate grammar rules to do parsing during inference. And then we give a connection between pre-training objective and the ability of this model to do parsing during inference. Any questions here? Okay. Let's go deep into. Okay, so let's go deep into one of the premier algorithms that is used to do parsing from a PCFG. So, starting to do parsing, either you could have enumerated all possible trees and just found the right one, which will take exponential time to do, or you could do something very efficient, which is called the inside-outside algorithm, which is a dynamic programming-based algorithm. So the algorithm has two major components. One is the inside probability, and another is the outside probability. Let's get deep into like what these are. Suppose you have a sentence like I have a car outside. The inside probability for a span and a non-terminal aims to find the likelihood that the non-terminal could have given rise to the subtree on the span. Or you can think of it as what's the probability that the non-terminal could be the head of the subtree representing the span. The outside probability, on the other hand, aims to look at the possibility of the coexistence of the non-terminal with the rest of the tokens. So what's the probability that if my non-terminal were representing the span, how likely it is that it could coexist with the rest of the words, I, car, and outside. And then the inside-outside algorithm is basically a dynamic programming algorithm where you first start with initializing the inside probabilities of one length spans. These are initialized by the token generation probabilities of the different non-terminals. And from that, you build on to find the inside probabilities of two length spans, which are functions of the previous inside probabilities and the token generation probabilities. And then you go for 3-length span, and finally you compute the inside probabilities of the entire sentence of 4-length span. And once you have computed the inside probabilities, you trickle down by first initiating the outside probability of a 4-length span to 1, and then trickle down to find the 3-length span, outside probability, then 2-length span, and a single-length span. So the exact computation here, I won't go into details, but I'll pick one of them later to explain relation to BERT. Yeah.
Each step take like the number of non-terminals possible complexity.
Yes. So that's I'll come there. Yeah. So each step will take for each span you have to compute for each non-terminal. Then each of these blocks require like number of non-terminal complexity, and that we'll go there later. Yeah. Okay, and then once you have all the inside and outside probabilities, you compute a span score, which is a product of the inside probability of the span and the outside probability of the span of the non-terminal that can best represent this span. And once you have that, you just return the tree that has the max sum of span scores. And you can show that under some conditions, this will return the max likely tree under the PCFG data. So for the example that we had before, for I have a car, this tree will return because the spans containing I have a car, have a car, and I have a car will be selected by this procedure. Okay. All right, so I gave you a brief on what the inside-outside algorithm is, but how does it relate to the questions that I had? Well, you can show that. Let me take this here. Yeah. This one? Here. Oh yeah, thank you. Okay. All right. So all the operations that are involved in inside-outside can be efficiently simulated by an attention head. The way to look at it is to look at this inside score that you need to compute for a non-terminal and span. And there's a scary looking formulation, but let's break it down. You break the span into multiple pairs of subspans. And for each such pair, you take the dot product, or you take the product between the inside score of the span 1 and inside score of span 2, but weight it out with the possible production rule that could have given these two spans. But if you look even closer, this can be given as a matrix vector dot product, where the matrix under consideration contains all the rules involving the non-terminal. And if you represent each of these inside probabilities of the span 1 and span 2 as an embedding, then you can represent the inside score as an attention score by careful key and query transformation using the inside scores. And this is what we used. So using this intuition, you can show that the inside-outside probability for PCFG with n non-terminals can be simulated by a transformer with 4 n attention heads per layer and NL embedding dimension, where L is the sequence length. And that's where I come back to your point that because each operation requires computation for n non-terminals, you require this 4 n attention heads per layer. And informally, the model will look like this, where the first L layers compute your inside probabilities and the next L layers compute your outside probabilities. Okay, so question is, are we done? No, because you require such a huge BERT model that depends on the number of non-terminals. So English is a complicated language. if you try to fit a PCFG to get all the rules correct, then you require a PCFG with 10,000 non-terminals to achieve at least 90% success in getting the parse trees correct. So if I go back to my theorem, I require like roughly 10,000 attention heads in each layer. So question is, how does the BERT model that has only 12 attention heads and 768 dimensions still predict the parse tree well? The point here is that BERT itself is okay, right? So BERT, if you remember correctly, BERT is roughly at 80% F1 score when trained on Wikipedia data. So we still have a candidate which has only 1600 non-terminals, and it can give you roughly 78% parsing. So we still have a candidate, but in order to further, but if we take this candidate directly, we will require like 1600 attention heads per layer. To further reduce, we use something called the low rank structure of the underlying PCFG, further compress the PCFG model that we have to have a more, efficient transformer. All right. So we use 3 strategies to compress the PCFG, the candidate PCFG. First, we separate out the non-terminals into 2 separate groups, the pre-terminals and in-terminals. The exact definition here is not necessary, but they were decided on the basis of where they appear in the PCFG tree. Next, we restrict the computation in each of these groups to a few pre-terminals and in-terminals. And the decision again was made on some sort of like frequency in the corpus. And then even when you restrict to a few non-terminals in each of these groups, we further apply low rank approximation for computations with this few selected non-terminals. And the graph on the right-hand side shows the effect of the second and third compression step, where for one of the groups, you could restrict the computation to 20 non-terminals and still achieve roughly 70% parsing score. And on top of this, you could reduce the rank of the computation to roughly 10 or 10 to get to even get like 70% success. So on these observations, we have this theorem that there exists a transformer that has 15 attention heads and roughly 1000 embedding dimension that can achieve 71% parsing score on English sentences. Any questions here? Yeah. Yeah.
How big are the norms on this transformer of the matrix?
That's a good question. So if you use softmax attention, yes, they need to be bigger. But yeah, but we showed only for linear attention, and we said that linear attention can be simulated by softmax attention. And for that, you require the norms being higher on a particular position so that you can simulate linear attention softmax. Right. So that's the way we went, but
have you trained the transformer with linear attention?
I haven't trained with linear attention for this.
Or like take an existing transformer that's been trained with linear attention, fine tune or train
that existing. No, but I guess we do controlled experiment where you train a transformer from scratch on PCFG data and then probe, right? For that, so that model had softmax attention. We didn't try linear attention, but might be fruitful to go and look into it. Yeah.
So you can just turn down the temperature parameter. Like, did you train the softmax with temperature parameter 1?
Step 1. Yeah. No, you have to make the temperature lower for it to go as close as linear attention, right? Yeah. Okay. All right. So the next question is, okay, we have shown that moderate transformers are good enough to encode grammar, and perform like approximate parsing at inference. But why should they even have the ability in the first place? Then in that direction, we show that the inside-outside algorithm is an optimal algorithm for mask-based pre-training under the PCFG grammar rule. Okay. So the way to think about it is as follows. If you have something like I mask a car, the way to find the word that can come in the mask is to first predict the non-terminal that can represent this span. And thinking a bit deeper, we found that this is exactly what the probability of the non-terminal can be, given the rest of the tokens. And that's exactly the outside probability. And once you figure out which non-terminal you could be present there, you could say, well, you can then predict which word can come depending on the token generation probabilities of the non-terminal. You can extend this logic to random 15% mask prediction, which is used for BERT. Well, there you have to show that, well, this mask patterns are spaced enough so that you can make this calculation. And you can also extend this logic to a span-based masking, which is also used in later BERT models. The thing to point out here is that we only know the inside-outside algorithm to be the optimal algorithm, to be an optimal algorithm for mask pre-training. We don't know of any other algorithms, so might be a good question to think about in the future. Yeah.
The optimal, you just say this is one algorithm.
This is one algorithm. Yeah. Yeah. Okay.
Yeah,
So
I have a question.
Directly to the experiment section. Given that we are in the controlled setting, we only train our model on some sort of PCFG data where we will generate a bunch of sentences from the PCFG data, and we pre-train a bunch of BERT models. In the paper, we have a lot of analysis on how things change with different size models. Here, I'll just focus on like a BERT-based train on the sentences. And then we probe the model to see if it has traces of inside outside. Yeah.
Yeah, so my question is like regarding your previous slide, what happens if there is no non-terminal generating that particular segment?
No, we don't have any questions.
Oh.
Right. Okay.
So can you hear me? Okay.
Okay, let's keep going.
Okay. So
yeah,
so we probe the pre-trained model with a simple classifier. And we stay true to what was being used before. We use contextual representations of word pairs. We train a very simple model to predict the common ancestor depth. To recall, I and have a 0, have an A have 1, and A and car have 2, and then you can recreate this tree. So the contextual representation that could use to train this model could have come from any layer of BERT. And that's what we did. We verified across all layers, and this is what the the success rate looks like across the layers. First, we observed that the model can achieve really good performance, like roughly 70 to 70% F1 on this data. And the yellow line is the one that is given by theory, which is roughly 71%. But then there are differences between what this model that we trained and what the theory predicts to be the optimal model to be. So it still says that, okay, there is still some more compression to be done on the PCFG data. On the other hand, we found that contextual representations help compared to the non-contextual or the token or simple word embedding. And it does much better than a very basic baseline, which is just creating right branching trees or just one-way branching trees. Instead of stopping there, what we did was we tried to probe for traces of the inside-outside algorithm. And we try to probe for the attention for the span score of each span, which recall that is given by a product of the inside and outside priority, represented by the best non-terminal. So what we did was we represent again span by the final layer contextual embeddings of the first and last tokens, and we verify whether we can predict for across all span lengths. And this is what we got. We could predict using a two-layer neural network with high correlation in comparison to a non-contextual or token embedding. So it still has, this means that it has traces for the different span scores. Furthermore, it does better at 2 length span, but it also does like pretty well at 10 length span. Okay, and yeah, so and there are many more experiments in the paper that tries to see if we are cheating here. So we had many sensitivity analysis to say if this is cheating or this is not, and we found that this small models, two-layer neural network and linear probes don't have the power to get this pretty well, without any help from BERT. All right. So the key takeaways from this half is that by data generation with PCFGs, we show expressivity of moderate size transformers to apply approximate parsing at inference. We could connect pre-training to this ability by showing that inside-outside is one of the optimal algorithms for the pre-training loss. And then we did a bunch of experiments to show that on models trained on this PCFG data, there are traces of span scores in pre-trained models. All right. So let's jump to the second half of the talk, which is trainable transformer and transformer. This work was in collaboration with Sadhika, Mangjo, and Sanjeev at Princeton Language Institute. And this paper is mostly built on the principles that we had before. Again, we know that transformers are pretty good. So we build a transformer and then keep on compressing till we reach something that can be doable in academia, or that can be simulated in academia. All right. So the talk has 5 major sections: motivation, and then I talk about the transformer model that we built, then experiments, and finally a conclusion. All right. The phenomenon that we're going to study in this half is in context learning, where you give the model a few examples of the task in hand, and it learns on the fly to perform the task by and then give the right solution to the query. This can be given, can be presented as 2 examples here, which is one is on sentiment classification and another is on topic classification. In the sentiment classification task, you could give a large model like GPT-4 a pair of sentence sentiment, a set of sentence sentiment pairs, and then ask the model to fill in the blanks for a given sentence, and it does it pretty well. You can give a similar example for a topic classification task. Now, there are multiple hypotheses on why you observe this kind of learning on the fly in large-scale models, but there are 2 major hypotheses in the community. The first hypothesis claims that LLMs have a very small, simple model inside, like a logistic classifier, that it can optimize using gradient descent during inference. And the second hypothesis is based on some sort of Bayesian inference and some sort of like favorable properties that are shared between the pre-trained data and the inference data. But for our talk, we'll only focus on the first one, which is LLM simulating gradient descent during inference. So what does it mean, simulating gradient descent during inference? Note that there is no explicit backprop involved. You cannot apply gradient descent to the large model that you are inferring. So let's take this example of language modeling. You have a large model, T1 transformer, which has T2 somewhere lying inside. And when you predict, when you ask input, machine learning is a useful tool. it updates the small model inside using gradient descent, and then uses the updated model to give the output. You could give this similar example for in-context learning for arithmetic operations, where again, you give a pair of XY pairs. The model updates the small model internally and then gives out the output. Now, this kind of mechanism or these kind of algorithms were pretty much well known before LLMs as dynamic evaluation and instance-specific meta-learning. So all this hypothesis is trying to say is that large language models encode this very intricate algorithms inside and use them for in-context learning or emergent properties at scale. So if I believe that this hypothesis is true, how would such a transformer look like? Well, it gets in the XY pairs as input. The first few layers apply forward propagation through the smaller model. Then it applies backprop and gradient descent on the smaller model. And then it uses a forward propagation through the updated model. Now, such a construction or such a transformer was shown to exist, at least theoretically, for T2, which can be as simple as a linear layer or a two-layer MLP. The question that we take here is that we take a leap of faith, and when we say that, well, a few steps of gradient descent on a very simple model is probably not going to explain all the emergent properties that you see at scale. So can we take a leap of faith and then construct T1 that says that T2 or the smaller model is as complex as a transformer, as a small transformer? We could use all the constructions to create a model, but that will blow up to a trillion parameter model, which is very difficult to simulate in an academic setting. So the question that we ask is, what has to change in T1 so that you get a reasonably sized model? And our contributions are threefold. We show that we propose a framework called transformer in transformer architecture that can efficiently simulate gradient descent on a small transformer model during inference. So our construction is orders of magnitude better than the previous constructions. Basically, we give a 1.3 billion tint model that can simulate one-step gradient descent on OPT 125 million and runs as fast as a 1.3 billion model that is there in practice. And our framework is very flexible, and it can be extended to other transformer variants like Pythia, Bloom, Llama, etc. Now, the reason that we propose such a framework is because of two motivations. First, we take this leap of faith and say that, oh, if there is a framework like this, maybe this implies some possibilities of many intricate algorithms that are present inside large models for emergent properties. But on the other hand, we wanted to provide insights into the best strategies for building these transformer models by explicitly imposing inductive biases into the architecture designs. So this is connected to the question that whether we really want to blindly scale our models to get performance, to get intelligent performance, or we want to have more intelligent design so that we can get this performance at reasonable scale. I'll circle back to this question at the end of the talk and see how many I could, how many of you I could, sway towards this question. All right. So let's go to how the transformer architecture was built. So this architecture was just built to be able to efficiently encode gradient descent, and I'll talk a lot more about like the system design that went into it. Okay, so we keep the construction backbone the same. The first few forward layers do forward propagation, and then backprop and descent, and then a forward propagation through updated model. There's one important question that we need to answer before we jump to the construction design. We need to give access to read and write access to T2 inside T1. And then the first question that comes is, where are T2's parameters? Can T1 simply store the T2's parameters as a part of its own weights? Well, no, because note that we are not allowing explicit backprop anywhere. T1 cannot change its own weights. So it has to only update the T2's weights through only activations, which it can change through inference. So then we jump back to what has been used in practice, where transformers have been shown to be Turing complete, and we'll try to build a Turing machine that helps to simulate gradient descent. So if we had the same idea, then let's say we look into one power module, then the way to simulate a Turing machine would be to have two explicit spaces in the module, one containing the memory of the one is a memory which contains the parameters of T2, and the other is some workspace where you copy the parameters of T2, work on it, and write it back. And this has been the main idea behind all the constructions that have existed till now. But turns out copy and write operations are very expensive. So if you want to simulate a copy and write, you have to use an attention module, which requires like 1.7 million parameters, which is very expensive to even use. So then the first design choice that we did was to remove all these inefficient operations. And the way you can remove the copy and write operations is to make the T2's parameters a part of the input itself, which it gets from the embedding layer. So the way the model would look like is there are a few set of unique tokens per module, which carry the T2's parameters from the embedding layer as input. And all the operations then become just transform operations on the prefix tokens that contain these T2's parameters, and the rest, the normal tokens that we have. So the first few tokens that you input to the model behaves like the training data that T1 uses to update T2, and the rest are used for evaluation or auto-completion. Okay, so yeah.
So is this like a sort of architecture?
Yeah, it's a prefix LM architecture, which is a prefix tuning architecture. Yeah. So yeah. Sorry. Yeah.
Context length will be like 125 mil.
No, because these prefix tokens are kind of they only contain the ones that are to be used in that module, right? So if you want to simulate a linear layer, then you only contain the parameters of the weight. So that's why it's similar to like prefix tuning LMs, where each layer contains its own prefix parameters. Yeah. Okay. All right. So internal layer design. So all you're trying to do is like encode gradient descent into the architecture. And for that, you need to look at like how the auxiliary model looks like. Well, it is a stack of transformer layers, which contains a self-attention block and a feed-forward block. And if you dive in a bit deeper, it is composed of 4 major operations: the linear, activation, self-attention, and layer now. So what we did was we created 3 simulator modules for each operation, a total of 12. And each simulator module is trying to update simulate the forward, backward, and a descent operation through these operations of interest. And finally, we just stack the simulator modules according to the configuration of T2. And that's how we get tint. So if let's say to give more details, like let's say we look at like something like linear, there's something like a module that does forward propagation through a linear layer. So before that, because we are going to use self-attention, let's look at what attention head did. You take in a sequence of input, have like query key and value transformation at each step, and then compute attention scores between different token pairs, and finally give an output that is a combination of the different value vectors. So going back to the auxiliary model of interest, we are trying to do forward propagation through linear layer. which takes in a sequence of input and gives a sequence of output, but each output is simply an affine transformation of the input at that position. But if you write it mathematically, it's just each element of the output is a dot product between different rows of the weight matrix and the input. But then that can be itself represented by an attention score between weight rows W and the input. So we can feed each row of weight into the prefix tokens, and we can represent the dot product as a attention module. Turns out this is good in theory, but not good in, but this doesn't help systems design, because there are two main issues with this. The first issue is that there is a blow up. The number of rows that you have to feed in to the prefix tokens leads to a blow up the sequence length. And then the more you blow up the sequence length, the more expensive it becomes to simulate the model. The second is like the dot product itself doesn't require many attention heads, but you have multi-head attention structure in these models, which also lead to some sort of parameter efficiency in these models. So to solve, we did two procedures. First was stacking, where you can stack multiple rows into the prefix tokens. And the second was to split the computation across different multiple attention heads and then sum them up using the attention module. So in this sense, like each row was split into multiple subparts. They're stacked onto the prefix tokens, and then using a query key value transformation, the final computation was done with a multi-head attention. Okay, so if you take the tint and if you magnify a module inside the four modules, you would see basically a self-attention that computes the output WXT. And I didn't go through the backprop and descent modules through the linear layer, but they would again look like two self-attention modules just computing the backprop, the gradient backpropagation, and the update of the weights. All right, so we could apply the same method for all the other 12 operations that are needed, but turns out if you do the same, you end up again with a trillion parameter model. So you have to modify gradient descent, and you have to apply approximations to gradient descent to come up with a 1 billion model. And I'll just give you some buzzwords for you to go and check out the paper later. The first buzzword is that self-attention allows some sort of duality that allows for efficient backward and descent operations. Without this duality, you have to use some extra unnecessary operations like the copy and write operations. We use a lot of zero-order gradient approximations throughout the model for efficient gradient approximations. We also approximate gradients in self-attention by some sort of like stop gradient. We parallelize computation in MLPs by some sort of like sub-MLP partition. And then again, here we use some sort of like low-rank approximations of all linear layers in tint to further reduce the number of parameters in tint. So all in all, with all of this in mind, with all of these techniques, we could get a 1.3 billion model that simulates one-step gradient descent on OPT. And the framework is pretty flexible to other transformers that have that are used in practice, like Bloom, Pythia, Llama, etc. All right. Given that we have a tint model, we quickly went and checked how good it is compared to other models. So what we did was we compared our tint model to an OPT model on which it was built on. We compared it to OPT model. So because we had approximations in tint, we compared it to true one-step gradient descent, and we also compared tint to a comparatively sized OPT model, OPT 1.3. And we found that tint achieves at least 4% better performance over the model that it was built on, so over OPT 125. We find that even with approximations, tint achieves arbitrarily close performance to true one-step gradient descent. And tint is competitive with comparatively sized OPT models and in context learning benchmarks. And these are very simple benchmarks. We started very simple and we haven't trained this model further, so we didn't go for like difficult in context models. Yeah.
How much does the length of the infer text, like how much does the sequence then lower for them? Because you need to pass that extra.
So original OPT takes like 2048 sequence length, and tint has 2500.
So
Yeah. But then the game there is that okay, you only feed in only the necessary parameters. So then that's how you kind of stop the sequence length blow up.
And how will you decide which are the necessary parameters?
No, it's the ones that are necessary for simulation of the operation that you want in the module, right? For example, if I just want to have WXT, like weight times X, I'll just fit in the rows of the weights as prefix tokens.
One step gradient descent is on the entire set of parameters, right? So how will you decide which set of parameters are crucial for the
We kind of run gradient descent on all set of parameters.
Are you saying that you, on different layers you feed in?
Yeah.
You adapt, you have different parts that were fed in
Yeah.
at different layers?
At different ends, yeah.
So you have a different prefix at every layer?
Edge layers. And that's what exactly prefix tuning is, right? At different layers, you feed in different parameters. Or different prefix parameters. Yeah.
Different depth you feed different parameters. and
Yeah.
That happens through forward, backward, and forward.
Yeah. Yeah, and so the changes that you can make in the backprop and descent show up in the activations or the token activation because that's what you use in the, yeah. All right, so in conclusion, we present a tint framework that presents a parameter efficient construction capable of simulating gradient descent on a small transform model. This shows the ability of moderate scale architectures to encode intricate algorithms for emergent properties at scale. But this also shows that for moderately sized models, maybe understanding inference may require understanding the training dynamics of a small transform model. In future work, well, tint was we started tint with the hope of an initialization framework that we start a large transformer, small transformer, and with the model's perplexity being better than the small transformer itself. And we got that, but we didn't go and continue to pre-train or instruction to tune it for better in context. Sorry.
Is it better specifically at the few shot tasks or in general on language modeling?
In language modeling, I didn't present the language modeling task, but you could do the same for Wikitext and Wikipedia dataset, and you can see that the perplexity drops by 1. So right at the start, the perplexity is better than the small model. So you have some benefits right at installation. We don't know like if you go and train it further, if it does better. But this provides an explicit way to pack gradient descent into the architecture. So this provides one way in which you can pack the inductive biases into the model architecture. So I want to end this talk by asking what other algorithms can you efficiently encode into the model architecture that can benefit its in context properties or emergent properties at scale, so that you don't need to blindly scale the model. You can still get this performance at moderate scale. That's all. Thank you.
Great, thanks. Thanks, Abhishek. Questions from the audience? We had a question during the talk. Would you like to?
Yeah, hey, can you hear me?
We can hear you.
Okay, great. So when you were discussing the inside-outside algorithms of optimality, you were mentioning that if you have some tokens that you don't know, yeah. So there was you were basically maximizing the product for I forgot how they're called there, for the NT, right? Yes. Oh yeah, that's right, the previous one. Yeah, so this one. My question is, maybe that range doesn't correspond to one NT, right? I mean, like if you think of it as a tree and those are like some leaves in the tree, they need not correspond to like a full subtree. it may be that these are like leaves that are sort of cousins in the sense that their parents, you know, are not the same. So do you get what I mean?
Yes,
I am
yes,
not sure what to do then. Like maybe basically the lowest common ancestor of all of them kind of contains some other tokens from the outside as well.
yes. So the point here is that it's one mask. Should I open this? Okay.
Yeah.
Come on. When
It's okay, you don't need this. What do you,
should I?
as long as we can hear you, which I think we can, yes. I think we
Yeah.
can hear you.
So yeah, can you hear me?
Yeah, I can.
So the point here is that okay, first of all, one mask they won't be.
You can mute your speaker.
So it will work.
Try.
Okay. Mute my speaker. Oh yeah, sorry. Yeah, sorry. If you can hear me. Yeah, the point here is that okay, you have one mask. You're not going to share parents with other cousins or sisters. And when you have random mask, you can always give some argument that they're not probably going to share many parents close to the leaves.
I see. I guess this is
The
mostly
issue comes when you have like span-based masking where both have an A kind of are masked together, or I have an A kind of masked together, or like tokens masked together. There, yeah, you have to do this kind of argument where you have to go to the common ancestor and kind of argue there, like there you have to argue somewhat like more together in some sense. But when you have like random 15% masking or random masking, you kind of
it's unlikely.
you kind of can say that the masks are kind of very well separated, so you don't have like this issue of cousins like sharing parents.
Okay, yeah, got it. Thanks.
Yeah.
Do you see any obstacle to doing next word prediction in principle?
Oh, so that's what so there is a paper by Yuanji and Jivan Ranju that try to do this for next word prediction. Yeah, this is basically say the same that the model learns to do dynamic programming over the course of broader for next word prediction. Yeah.
More questions from our audience or online? I'll throw out a sort of anyways, I mean, as I'm sure you know, there's this problem in biologically realistic neural networks that brains don't do back propagation. And now you have a way of doing something like gradient descendant back propagation without back propagation.
Yeah.
So I wonder if there could be any relevance for that.
I don't know. I don't know. But again, like you can incorporate any module that you want, that you feel that the model might not learn on its own.
Right.
You can create modules that are like this transformers and whatnot, and you can incorporate directly to the architecture. Yeah.
So if you wanted to make a transformer in transformer in transformer, would that just involve a further 10 times blow up in the model size?
Yeah. But then oh yeah, so also the gradient descent algorithm is very easy to encode. If you go for something else like Adam or whatever, these things will blow up. Like, I guess you can make some connection between how much memory and everything you require for one algorithm and how the model blows up.
I mean, you're only doing one step.
Yeah. We're also doing only one step. If you do multiple steps, then even that blows up. So
Can I interpret this architecture as this higher level model choosing between lower level models, a continuum of those, and is this a legitimate interpretation?
yes. Yeah, so it's like a very large model, not learning things on its own, but maybe having a small model that learns everything and then just builds on top of the small model.
This nicely harmonizes with what psychologists think human brain is doing. That it doesn't have a common model, but it has a many of models, and it chooses which one to use depending on the context and how much time, resource it has,
Yes.
and so on.
Yes, and that's, I guess, the main reason why this hypothesis even came into being. Like, people tried to make connections between large model and a brain, and I guess that's the point, that okay, the model kind of decides which model to use when it sees the context, and then learn on the fly.
So if you take the transformer and transformer and you fix all of the actual parameters of T1, the outer model, but you enable the parameters of the inner model, like the prefix prompts, to be tunable, and you run gradient descents like on the outer model. Does this do anything reasonable?
Yes. So that's the reason why so if you look at tint, it has like two models basically. Like, it has this prefix tokens, which is like small model parameters, and it has and both of them are tunable when you tune the entire model, right? So the hope there is that, okay, when you tune this, the model can change the algorithm that it wants to. It can start from gradient descent, but it can change as it wants to, and it can also change the base model on which it's built. So that was the main reason why we wanted to come up with this architecture. We haven't, because we don't have resources. So once we have resources, we'll start. So initial experiments so that it's trainable, at least on a very simple setting, but we want to instruction tune or whatever to see the real effects of encoding such a model.
It can't change the base parameters, right? It can change gradient descent to something else, but the tokens are fixed.
No, the tokens are stored in the embedding layer of the thing, right? The embedding layer is also tunable, right? You just feed in like port parameters. The prefix tokens are stored somewhere, and that's the embedding layer. So you can change them, right?
Maybe this was part of your previous answer, but is there a task that you can train T1 ab initio to get the T1 to become the emulator? I mean, it seems like if you train it on the literal thing you described, it would work, but it would require vast amounts of training data.
I don't know. I don't know, but even I don't know if I train a T1 of this size, if I just initialize it from scratch and then train, if it gets back this model architecture, or if it gets something else. It's unclear.
But it's relevant, it's practical relevance, or any relevance there must be some way of training to get it. So more questions from the online audience? More questions here? Well, if not, let's thank Abhishek for really very interesting talk. So we have we're skipping next week, and then the following week will be the last of our series this semester. Catherine Collins will speak about evaluating language models for real mathematics problems. So I look forward to seeing you all there. Thanks for joining us.